Hi everyone, thanks for coming. Today we're going to see a presentation from Travis Norris and some Markforged engineers on 3D printing and its kind of applications in FIRST Robotics.
So if you guys each want to go around and give your name and then a little bit about yourself and what you do at Markforged, that would be great.
Sure thing. Hi everybody, I am Travis. I'm a software engineer here at Markforged.
I'm Caitlyn. I'm on the materials print team at Markforged. Make printers print well, basically.
I'm Madeline. I'm on the print system engineering team. And I fix things. That's kind of my main role.
My name is Lee McMillan. I'm also on print system engineering. And we're jack of all trades, master of none, make things work for our customers and yeah, fix things.
Thank you. So I know you guys have something prepared for us, a presentation. So if you guys want to get that started, then that would be great.
Great. Yeah, we'll dive right into it. We here at Markforged, we know there's a lot of teams in FIRST Robotics that may be familiar with some of our printers and some of the things that we do. But we wanted to give you an idea of some of the other great things that Markforged does, as well as some more technical details about additive manufacturing and 3D printing and all kinds of things like that. So we'll get started. First off, a little more introduction. I'm Travis. I went to WPI with a study in robotics engineering. Outside of work, I am a coach for FRC team 2423 here in Watertown, Massachusetts. And I'm a software engineer on the IoT team. So I help users interact with their printers kind of on the device itself. I'll be starting off with just a little bit about what is Markforged. You may have seen our printers, you may have worked with them in the past a little bit, but you may not know why we are the company that we are. We specialize in certain types of 3D printing, and in the additive manufacturing space, there's a lot of different things. So the origins of 3D printing go all the way back to the 1980s with what are called binder jet systems that are similar to like 2D laser printers or like photocopiers. In the 1990s, you had these laser technologies using selective laser sintering. And then around 2009, there was this technology called FDM, fused deposition modeling, which the patent expired on. And that's the kind of plastic extrusion that you see in a lot of hobbyist and consumer 3D printers. So around the 2010s is when all these kind of hobbyist printers started popping up with people making their own, printing printers that printed other printers, and lots of cool technologies and things that people were developing and coming up with at the time. That's where Markforged kind of came from. We are mainly an FDM printing company. And so we print with an extrusion of plastic or other materials onto a bed. But the kind of innovative thing that we brought and what we're really well known for is our continuous fiber reinforcement. So on the right-hand side there, you see a couple of different examples of parts printed with fiber around the outside. So these are carbon fiber, fiberglass, and Kevlar and other materials that really add strength and stiffness to the parts that makes them not just suitable for hobbyist applications, but real world industrial examples, and gives us really nice quality parts that we can use in industry and in all kinds of different applications. In general, the things that Markforged really strives to do, we strive to make sure that the part is the product. We want to make sure that every part that comes off our printers is high quality, is ready to use. And we want to make sure that our customers have a good experience that works every time and is reliable. So you can trust your printer to do what you set it out to do. And we want to make sure the experience is easy with the mindset of just press print, where you can load up a file, whatever it is, even if it's very complicated, a challenging print to accomplish, we're able to just press print and it'll work out for you. As well as with our products get better with age. So as our products develop, we release new features, new materials, new things that it can do over time. meaning that when you buy the printer initially, you can expect improvements and things that it can do in the future. And that's really where Markforged has kind of stood out and excelled in the past couple of years. You may be familiar with our kind of desktop 3D printers, but those are just the smallest printers that we offer here at Markforged. We have our industrial 3D printers that come with more, a larger build area, more sensors, and more accuracy that you can get there. We have our Metal X printer, which is able to print metal, which Caitlyn is going to talk a little bit more about later. And then we have our recently released FX20, which is our largest printer that's capable of printing high temperature materials for aerospace applications and lots of very large, very hot, very cool parts. Along with that, we have all kinds of different materials. So Onyx is our flagship composite material. It's a nylon based plastic with chopped carbon fiber in it. But we've also recently released other materials for our composite printers, including Precise PLA, which is targeted for the same high quality printing capabilities you'll get with Onyx, but at a lower cost for prototyping and things like that. And then recently, just this week, launching Smooth TPU, which is like a flexible material that you can print as well. Plus, we've got all our different metals, coppers, and different types of steel for different applications, and all kinds of crazy materials that are fun to see. And then some other exciting high temperature plastics and things coming down the road, and always more on the way. So there's lots of things that Markforged is working on, researching, and able to kind of release to our printers and to our customers. And it makes it a really great place to work, to be able to see all of these cool things in development and all of the cool technologies that our team is working on. As a software engineer, I of course would love to talk about Markforged software. So the goal of our software with that just press print mentality is that it does a lot so that you don't have to. Your experience with the printer may be just seeing your parts, pressing a couple buttons, and it's ready to go on the printer without you having to worry about it. But in the background, there's a lot of things that we are managing as the software team. So the motion control and path planning of our slicer, which turns the part into the actual printer instructions. You've got material specific settings, different temperatures and speeds and things like that. We've got print issue detection. If there's a jam or your part doesn't print correctly, we want to be able to detect that and maybe save your part, save our printer, and things like that. Managing all these part files, being able to inspect your part as you're printing, as well as printer maintenance to make sure that it's kind of up to shape and that it's up to date with all of our latest software and all of our latest features. So lots of things that we do that our software kind of makes easy for the users, and we want to make it a seamless experience. So I'm gonna walk through kind of an example of what it looks like to print a part here at Markforged. I'm going to start by opening up an STL file, which is commonly used, can be exported from most CAD softwares. And you can see it here in our build plate. And all you have to do is go and select what type of printer you want to use, what type of material. There's a couple of basic settings to kind of tune the strength and tune the print time. But once you're ready, you can save that part and it's ready to go. You can also take a look inside of the part if you wish to see each individual layer as the print is being built up. This is especially useful if you're printing with fiber. You can see the reinforcement, like where the fiber will be laid in the part. If you're printing with supports and where they might attach to the part itself. So it really gives you a good inside look at how you can expect it to come out. And then once you're happy with that, once you're ready, all you have to do is click print. It will export it into this little build plate. You can choose your printer. As you can see in the office here, we have a ton of printers that we can choose from, and hit print. And in the background, it's doing all of the processing, all of the path planning and slicing, and going to send that off to the printer and get started. So it really makes it a seamless process for users to turn their 3D models into real parts. And it's going to start printing and going right there. Once the part is done printing, though, you may want to go and make sure it printed accurately and take measurements. So sorry, I switched slides. While we're on the printer, there's a lot of things that our printers can do to make sure that they're up to date and ready to print. All kinds of maintenance features and detection features if it's a jam or a printing issue that we can solve. So there's lots of software that lives on the printer that helps kind of diagnose and helps fix some of these issues to make sure that they're up to date and ready to print. And then once your part is printed, you may want to go back and make sure that it was printed correctly. And oftentimes that's hard to do with a lot of parts, especially if they have fiber reinforcement. The outside will be just a plastic shell, but on the inside you have all of your fiber that gives the part its strength. And so we have a tool called Blacksmith that can go in and inspect the part as it's printing, verify that fiber is placed in the correct part, check dimensions and accuracy of the printer. And this is really important for a lot of our customers who need to trace each part, need to make sure the quality is accurate once they get to a kind of production level where they're, depending on these part strength and that kind of stuff. So, of course, all of this, it sounds like very cool software, but it all depends on the full team. I'm sure all of you robotics students know that nothing gets done just in software. It takes work with the print teams and the mechanical engineers and the electrical engineers to understand the sensors, understand the settings and things that we need to be using to make sure that our prints come out as well as they can, to make sure that our machines are up to date and being well maintained, and to make sure that our customers can be successful. So it always takes a lot of collaboration, and I'm really thankful to work with so many other smart people who know way more about how the printers work, know more about materials and all this stuff, because I'm so impressed by every time I get to work with someone who's like, oh yeah, we solved this problem in this really creative way. So it's always great to work on that kind of team where we get to learn about different disciplines all the time. Awesome. So speaking of other teams, I'm going to turn it over to Caitlyn.
Cool. Maybe
Sure.
this way. All right, cool. So I'm Caitlyn. I'm on the materials print engineering team, but some background. I did my bachelor's at Wentworth, which is in Boston, in electromechanical engineering. And then I did my master's in 3D printing at the University of Nottingham in England. I'm a materials print engineer. I improve how our printers print. I improve materials offerings. I work towards just like either improving part quality, bringing new features, bringing new materials. All of those things kind of fall into the print engineering domain. I'm mostly focused on composites, but I'm going to be talking about our metal system today. So like printing metal, like how do you go about printing metal? So some of the biggest issues with printing metal in an FFF system is that plastic melting temperature, like even like higher temperature thermoplastics, usually like you're looking at like less, like around 350 F. And that's acceptable for the technology. But when you're looking at metal melting temperatures, steel melting temperature is 2500 F. So when your printer, if you try to go much higher than 350, you can't do it. How do you manage to print a part in a material that has a melting temperature of 2500? And the way that we approach it is by adding a plastic material basically into the mix of our metal filaments. And then when we are actually printing and heating, by heating to the melting temperature of the plastic, the material is still able to flow through the nozzle with the metal particles kind of just going along with it instead of actually the metal itself having to be melted. So then following that step, you have what's called the green part, which is what you take off of like the printer system itself. And that then goes into the wash, which is a different stage of the metal process. And after you have the wash part, you have a brown part, and most of the plastic has been washed out by the special solution in the wash. Then it goes into a sinter, which is 5 times hotter than your oven at home. So it goes in there. It gets very hot and it causes all of the metal to fuse together. This also means that there's lots of considerations with printing metal parts, like you have to scale them up when you print them because they shrink down once there's nothing else there when they all fuse. And so that's the gist of how metal printing works. So you only have metal, all of your metal is fused together now instead of just floating there like before. And then once it's cooled, you have your whole metal part that's just metal. So now designing for 3D printing.
All right, next slide. Okay, so I'm Madeline, a little bit of background about me. I did my bachelor's in mechanical engineering at Boston University. Favorite pastime, I really like doing jigsaw puzzles, Legos, anything that I can kind of build. That's kind of the mechanical side of me that I enjoy. My role here is print system engineer. I said earlier, I fix things. I'll expand on that a little bit more since print system engineer is very vague. So Leah and I are actually on the same team. We're both print system engineers, and we take a customer-centric view to engineering. So we help make sure that the customer can service the machine, they can maintain it, they're able to go through different utilities, and it's easy to use, basically. So it's in addition to software like Travis does, but making those workflows really easy to go through. Next. So I'm going to talk a little bit about designing for 3D printing. This is very basic. This initial one here, part orientation, trying to take the part that you want to print and orient it in such a way that you are minimizing the supports. I'll go a little bit more into that next. So this is something, if you're familiar with 3D printing, that you've probably seen a lot of, is that typically overhangs at 45 degrees are able to be self-supported. However, something that's a little bit more advanced that I wanted to touch on here is layer height. So in the upper left-hand corner there, this is showing that at different layer heights that you can achieve actually different, like better, steeper overhangs depending on your layer height. So the taller your layer height, the less your overhang is supported underneath, and the more you're going to have some drooping, and you might not even be able to get to 45. You might only be 40 degrees from the vertical. However, when you go to those lower layer heights, say 100 micron, 50 micron, you're able to kind of stack those up better in such a way that they're supported by the layer below it. So you can actually get overhangs that are a little bit steeper, maybe up to 50 or 60 degrees. This will also vary widely on the material that you're using. So like PLA is very good at bridging and cooling almost immediately. We have other materials that droop and tend to be more viscous or less viscous when printing. Next. So speaking of bridging, so PLA really good at bridging. Some other things here that this is, how do you get around having supports? So when you're designing your part, you want to avoid supports. Like I said, the orientation matters, but also when you're designing it, there are little tips and tricks that you can add in to try to avoid those supports being generated. So anything at a 45-degree overhang angle, most slicing software, including Markforged Eiger, will automatically detect those and not create supports. So you can do this kind of teardrop hole on like archways or holes on the right-hand side, and that way you will not have supports. Supports can be a pain to take out. Occasionally those supports are unavoidable. So next slide. So this is a very famous part. It's called a benchy. It's a boat, and it is used as a benchmark part for 3D printing. So you can make sure you've got like your layer adhesion tuned correctly. And it's just a good baseline for different capabilities of a 3D printer. So typically this part is printed without supports because PLA is pretty good at bridging. However, I want to give this example if we were to print this in metal. Metal would not be able to do these overhangs. Go next slide. So we'd have all of these supports here. So this is a view from Eiger that I took. On the left here, you can see the part kind of in like gray, and the purple is the supports there. So it might be a little bit hard to visualize here, but that kind of purple column, you would not be able to remove this support. So we call this trapped support. It's undesirable, especially if you're printing in metal. With plastic, you can get away with it. You kind of tear it apart, but with metal, you're getting much higher strength material and you're not going to be able to do that. So the way that we can get around this is by breaking up those supports. So there are cubic or radial supports. So in this example that I have here, it's a cubic support, breaking up that kind of giant block of supports into smaller pieces. And so that will actually be able to remove them. So there are kind of a lot of advanced different ways to do this. You can create your own supports that you're able to, you know, slide out. And there gets much more complicated if you really want to, but things that require supports, there is almost always a way around it that you can still have a support if you need it, but also get it out, which is important. Next slide. All right, so just a little bit on minimum feature size here. So the bead of plastic has a certain width to it, and that limits how small of features that you can print. Think of like on a penny, the raised writing. The width of those letters, that's the minimum here. That's what I'm getting at. So we have minimum like post diameters, engraved and embossed features, and whatever material that you're printing with, and the nozzle diameter will determine how small typically your features can get. Last slide. So putting it all together, this is a like similar to a benchy, but more of a qualitative look at how does your 3D printer do with dimensional accuracy, with bridging, with hole size, overhangs, and just a good like 3D printing part to benchline your printer. So you can do kind of apply the tips and tricks when you're actually designing the part, and then when you're slicing the part, you can take a look at those supports. Yeah, that is a little bit of some design for 3D printing.
All right. We're getting a zoomed in view. Again, my name is Lee McMillan. I'm going to talk about kind of some of the cool, fun stuff that you can do with 3D printing, and what are some of the cool things that you can print. Go ahead. So my name is Lee McMillan. I got my bachelor's in materials science and engineering from the University of Arizona. Bear down, go Wildcats. Doesn't make any sense, but I go with it. Like I said earlier, I'm a print systems engineer on the same team as Madeline. So, you know, customer focused mindset of, you know, maybe mechanical design this really, really cool thing, but once we put in all the motors and electrical components, it is like physically impossible to maybe go do maintenance on something or whatever. And so thinking about products and how they evolve and how they're going to be used in the future, and by people that are not engineers like us that, you know, eat and breathe this stuff. One of my kind of favorite applications is being able to print more printers. It was kind of like one of the original things that you could do with printers. It was really cool. And there's even more you can do with it. So next slide. You can have functional prints that are fun and cool. The GIF on the right was one of these neural containers that is on Thingiverse that one of my coworkers, Ross, printed in metal. And I've like dropped that, and it's just got this fantastic solid weight to it. Next slide. You can, of course, make tools and tool racks and organizational boxes and whatever. I've designed my own spice rack so that it like magnetizes to my fridge so it doesn't take up counter space. I printed it in PLA, and then I sprayed it with a food safe coating, because 3D printed parts are not food safe. Even if, say, like PLA is technically like FDA approved, the process of 3D printing makes it a porous surface, which means bacteria can grow on it. So 3D printed stuff is not food safe unless you coat it. Just a heads up. All right, next slide. And it can also be used for art and mementos and everything. So this is a backpacking trail that one of my coworkers spent, 10 days, or not 10 days. I think he was there for a week. And so you hike and you stop at these huts, and just had this crazy long hike through Iceland. And to commemorate it, he designed this, which was really neat. Of course, toys and games and random fidget spinners On any given day, I like look down the line of desks at my team, and we're all doing something, fidgeting with a fidget spinner, or, you know, bobbing our heads to the music. So that's some fun stuff. These are some other cool things. The marble track is, I think, from a YouTube channel. My coworker, Austin, who was initially supposed to present today, has been making Guitar Hero controllers that he prints and like gets them all actuated and gets the buttons to actually like click and function like the original ones. And then they can be entirely custom. And then some of the kind of more out there applications is you can 3D print buildings. So some of these are out of concrete, like these ones here. One of the kind of original ones a few years ago, they printed, installed all the like appliances, electrical, plumbing, like it was a fully functional house within 24 hours in the middle of the Siberian winter. It's really cool, look it up. But one of the neat things about these things is they can be printed as needed. You can change the design, and then a lot of the like electrical conduits and plumbing and everything can be installed as it's being printed. I mean, once you have I can talk about this for a while, so I'm gonna move on to the next thing. And then one thing that I think is interesting, it's not maybe quite robotics related, but near and dear to my heart is materials and how they can be used in 3D printing. But one of the things that exists is a material called bioglass. And you can 3D print bioglass. And so bioglass essentially is if someone has had an accident or like even degradation in their jaw from losing teeth, is you can take this material and implant it in the space that needs more bone. And it is similar enough in the composition to regular bone of, I mean, again, if this is interesting at all to you, look it up later. It's fascinating and really cool. But it's essentially glass, like you would think of like glass or a bowl or whatever. And you're able to like implant it in the bone, then it interacts with the like physiological fluids that like activates the surface, and it is made up of, you know, all the calcium and all the nutrients and stuff that you need to make bone. And growing new bone takes ages, and it's a very involved and like energy intensive process, like 6 to 12 weeks and even beyond that. But essentially the bioglass interacts with the body, and it gets to a point where it is the hydroxyl carbonated apatate, which is very close to hydroxyapatite, which is essentially the hard calcified bone. And in terms of, I know I'm going over, I will be very quick. But in terms of bone growth, you have osteoblasts and osteoclasts. And essentially the osteoblast goes running around looking for all the components to make bricks, puts them together, mixes them up, bakes them, and makes bricks or bone, essentially. And the osteoclast will break down the bone and essentially put it back into the like formable, movable components. And so like this is going on all the time, depending on how you use your body and how active you are. And it can be a very like long and intensive process, but with the bioglass inserted, it's essentially, you pretty much have bricks that are already there. So they don't have to like get all of the nutrients from your marrow to make the new bone. They can go, hey, this is similar enough. The osteoblast can take it, break it down, change it a little bit, and hand it back to the osteoclasts can take it, hand it back to the osteoblasts, and then over time, the bioglass is reabsorbed and then regrown as regular bone. And it's really cool and fascinating. And we're over time, so I will save the rest of my comments. Yeah, there's a ton of different applications. There's 3D printing in fashion. There's 3D printing in food. Of course, robotics, any kind of thing like rapid prototyping. If you can think about it, you can probably 3D print it. 3D printing might not necessarily be the best end application, but in terms of getting an idea out there, getting your hands on it, and iterating and designing it, it's pretty awesome. So.
Yep. Awesome. So
okay.
that's what we have for you today.
Okay, thank you guys so much. That was such a great presentation. That was really cool. We'll open it up to some questions. Okay, here's one. For each of you, why did you choose to be the type of engineer that you are?
Sure. So I started out in robotics, and I did all kinds of things, but I really found that software engineering to me is just like solving puzzles all day. It's a lot of fun little challenges that you get to work on, and it's always something I found enjoyable and entertaining. So that's kind of why I stuck with it, but I still like the mechanical and electrical side as well. So that's why I work at a company where there is so much hardware that I get to interact with.
I kind of fell into print engineering and 3D printing in general in my last year of my bachelor's, and then I read through it, and then I just really love and am passionate about 3D printing and printing, and so it's just the section that I fell into and like the part that I enjoy.
Yeah, I'm similar to Travis. I love problem solving. That's why I got into engineering, specifically mechanical engineering though, which is what I got my degree in. I got into that from honestly like playing with Legos when I was younger. Connects, just building things with my hands. And that's what really drew me to mechanical engineering.
Yeah, and then I picked engineering for similar reasons. I thought about it as people would literally pay me to solve problems and solve puzzles. And then with material science, there's just a lot of cool stuff out there. My department had a little booth that had a little tiny superconductor, which essentially it gets cold enough and it will lock like magnetic field lines in place. And so it will levitate's not quite the right word. But that was really cool, or like shape memory alloy where it was a spring and then they bent it out and then they had a lighter and when it waved it under and then it went back to a spring. And I kind of thought that is so cool. Like, let's see what we can do with that. But current position, I love materials, but I also want to be hands-on and see like, okay, we have this cool material. What can we do with it? What can we make? And yeah.
Thanks. Does anyone in the room have any questions?
And then we also saw that Michael Thompson raised his hand. So if you could put the question in the chat, we can answer that. Or the Q&A section. But do we have any questions from the class?
I have one.
Okay.
So why don't y'all use parts from y'all's printers to actually like make the printers?
How do we, what?
Do we use parts from printers to make our printers?
We use some, so some of our printers have 3D printed components to make them, yeah. Potentially like covers for different things or handles. But yeah, it's definitely a consideration of what can we do that makes sense for 3D printing, because making sure that your application makes sense for 3D printing is one of the main drivers of, does 3D printing this make sense, or is it cheaper, faster, more efficient to use a different technology?
We do use a lot of 3D printing at Markforged for different like fixtures. So I know a lot on the materials team for a lot of just like force testing, the Instron, we use a lot of 3D printed parts that we custom make for the application that we need.
Oh, thanks. Any other questions, guys? Coach has a question.
So you mentioned you showed two types of plastic at the beginning, PLA and smooth TPU, I believe.
Mm-hmm.
Can those be printed on the Mark II?
They can be printed on the Gen 2 Mark II. It's specific to the type of extruder that came with the Gen 1 Mark II versus the Gen 2 Mark II. So if you have a Gen 2 Mark II, yes. If it's Gen 1, no, unfortunately.
And you can tell that by one, either looking at the extruder, or even easier, if you look on the back of your printer where there's this big sticker that has the device ID, it'll say Mark II and then parentheses Gen 2 underneath.
Question from the chat was, how would you clean the carbon fiber nozzle?
Can you clarify by what you mean? Like, did you have a fiber nozzle jam? Is that the ask? Or is it like what do you use to brush off the nozzles?
I think they probably meant the second one, but
Both.
oh, he said both. Sorry.
I can take that. So you said the second one for how would you brush off?
He said both in chat.
Oh, sorry.
So for fiber nozzle jam, we have support articles on our website on the process to go through on that. As far as for the second part of the question, how to wipe it off, the accessory kit that comes with any of our printers includes this black plastic brass brush with brass bristles. Oh my goodness. That you can just wipe the bottom of the nozzle off with.
Yeah. Sometimes, depending on how much use it's gotten, you got to really be aggressive about it. So like bolt the print head and don't put too much pressure on the print head, but sometimes you really have to scrub, especially the plastic nozzle too.
It also helps if you heat the nozzle while you're doing it.
Yep.
That's
Don't burn yourself.
basically. Don't burn yourself, but it's much easier to get plastic off when it's warm.
I think, are there any other questions from the room or from the chat? Great. Well, that was really great, guys. So thank you so much for that. It was really, really helpful. And I think it was really eye-opening. And hopefully a lot of people in the room and on the chat are now interested in 3D printing, a little bit learning more about it. So yeah, thank you.
Thank you. Yay.
Take care, y'all. Thanks so much for having us. Feel free to reach out with any questions and check out our website for all the materials and printers and all that stuff.
Thank you. Have a nice day.